Hello everyone. Let's try another example here, taking a look now at some dynamic questions where we're considering two dimensions. Here we have a situation where Peter is pushing a 30 kilogram box with 200 newtons west. Sally, with her green dress, hope you guys remember what that's from, is pushing the same box 300 newtons north. There is friction acting on the box. There are three things that we want to do with this question. One is to draw a free body diagram. The second is to determine the result of Peter and Sally's forces combined. And then C is to determine the force of friction if the box has an acceleration of 4 meters per second squared. So let's first of all start by drawing our box. So I'll have my box here. And I want to draw a free body diagram with this. I'm going to try using a different tool rather than the arrow tool that was being used before. So we know here that this box is going to have gravity acting on it and the normal force acting on it from the ground. And that's going to cancel each other out. The hard part is how do I include those forces along with the force of north and west? If I'm looking at this particular situation and I imagine that north goes this way and west goes this way, then that means that really when I'm taking a look at gravity, it's going down into the page. And normal force would be coming up towards your eyes. And I can't really draw that. That's very difficult to include. And I haven't even talked about friction yet. So what we can do then is we can look at this from a bird's eye view. Imagine you're looking down at the box towards the ground. The ground is underneath the box, and you're up in the sky. The force of gravity pointing down is pointing, like I said, into the page, and the force normal is pointing up towards your eyes. Well, we know that those two forces cancel each other out. So in some ways, we can kind of ignore them, which allows me then to just focus on the forces going up and, the force going north and the force going west. So we know that we've got one force like this going north. You know what? I am going to move that because it'll, whoop, that's not what I want. Come on. Let me try this then. Let me try that again. We know that we have this force pointing north. There, that will feel a bit better. And we also have a force pointing west. So like that. Now, hopefully what you can recognize is that this box will want to go in this kind of direction. And so when we start including friction, if you remember descriptions of friction, friction acts parallel to the surface, so parallel to the ground, but in the opposite direction of motion. So if the motion is this way, then we know that friction, and I'm going to use a different color for friction this time, I'm going to use yellow, friction will act in this kind of direction. And let's see if I can label these. I'm going to call this F1, and I will call this one F2, and then this one over here, this is the force of friction. Alright, so that's our free body diagram. That's really our answer for A. Then we're taking a look at B, determine the result of Peter and Sally's forces combined. Well, really, I am just wanting to take a look at what is the combination of this force and this force. Now, hopefully you can recognize that these two forces are not in the same direction, so it's not as easy as just simply adding the 200 and the 300. I actually have to do some two-dimensional work here. And so it's really that I have to go back into the idea, what we've done in the past, is that I have one force acting like this, and another force acting like this, and I need to find the result that goes like that. Ooh, that's a bad arrow. Wow. Alright, so really the idea now I have is that this force going west is 200 newtons, and this force going north is 300 newtons. Let's move this one over a little bit. There we go. And so hopefully you can recognize now that I'm looking for what this force here happens to be. So I'll be using Pythagoras to figure that out. Alright, so we'll use Pythagoras. A squared plus b squared equals c squared. And we'll plug in our values of the 300 and of the 200. And hopefully you can see that it'll calculate it out to 361 newtons. So this is the equivalent that this box is being pushed in this kind of direction with 361 newtons. Hopefully you can also recognize that we're going to need to figure out what this angle in here is. So we're going to use tan. And so what I'll do is I'll just put the angle right over here. Alright, so then we get an angle of 56.3 degrees north of west. So I just used tan to try to figure out what this angle here is. So what I'm going to do now is I'm actually going to adjust our free body diagram, and I'm going to get rid of these two forces and just kind of indicate a force like this. So I'm going to get rid of this force here, those two forces, and I'm going to draw in the result of this force here. And so what I get is this dotted line, and I'm going to call that really the applied force between both Peter and Sally. So I'm just going to call that FA. And you're going to notice that I'm going to use that terminology quite frequently now, where if someone is pushing or pulling something, I will call that an applied force. And so we'll call this the applied force, and it has a value of 361 newtons, and this is the angle. So that is the answer for B here. And then now when I'm determining the force of friction, well, the nice thing is that these two forces are exactly opposite to each other. I do not need to do any angle work. It is just purely either addition or subtraction. And so if it's asking me to find the force of friction on the box, I want to know what this value is. The key to this particular problem is that it gives us the acceleration and it gives us the mass. If you have those two values, you can find the net force. The net force is all the forces combined, in other words, this one and this one. We already know that this one is 361 newtons. So if our net force happens to be 461 newtons, it would make sense that this is 100 newtons, just in the opposite direction. So let's figure out what the net force is, and then we can compare that to this 361 newtons. Alright, so here I've got the F net equals ma equation. We want to put in the values for mass and acceleration. So in this case, we have a mass of 30 and an acceleration of 4. And so now, when we calculate that out, we can see that the net force is going to be 120 newtons. Okay. So what we can do now is that we can see that Sally and Peter together are pushing with 361 newtons, but the box is acting as if there's only 120 newtons. So where does that extra amount go? They're pushing with 361, but it's only as if they are pushing with 120, or it's accelerating as if it's 120. Where that extra amount has to go into the force of friction. So now what we can do is we can use our other equation for F net, and that it's all the forces combined, and we can try to figure out what that friction force is. So what I've got now is that the net force is the combination of all the forces put together. I'm just going to move these over a little bit. Oop, I don't need that. I don't need two of them. Just move this over. And so this equation now, I have two forces, Fa and the force of friction, inside this. So I am going to rewrite that. Oop, hold on. Copy, paste. Here we go. The forces that I have now are F A, the applied force of Peter and Sally, and, oop, that's not what I want. I wanted that. Here we go. The force of friction. Here we go. And so from here, we can now put in the value of our F net, because we just figured that to be 120, and we can put in our applied force value. So that's going to rewrite as 120 equals the applied force of 361 plus our force of friction. And so hopefully you can recognize that what I'm going to do now is I am going to subtract the 361 over to the other side. And we'll get a negative. And it makes sense that the force of friction is going to be negative. It's going to be in the opposite direction, that of the applied force of this 361. So when we calculate that out, we're going to get 241, or negative 241. Force of friction is going to equal negative 241 newtons. And so now we've got our answer here. It's going to do it for me. Do I get a box? Oh, but it's filled. I don't want a filled box. Alright, I have to try that again. Fill. No fill. There we go. Let's try that again. Whoa, that's rather interesting. Yeah. Interesting. What is going on now? Why did it give me a wonky box? Now it wants to move that. No. Oh, oh. There we go. Haha. Alright. So I hope this will be helpful. I have an assignment for you that will deal with some of this, where you have to deal with forces on 2 dimensions, and to also include friction. It won't be a lot of questions today, but I want to be going through this rather intentionally, so that things will make sense for you. Alright, I hope you guys are doing well. Tomorrow is an admin day for me to be writing report cards, so you'll notice that up on the website there is nothing for you to complete tomorrow. And then Friday, of course, is Good Friday, so there'll be quote-unquote no classes. So we'll be back on the website on Monday. All right, hope you guys are doing well. Talk to you soon.